Welcome to Module 10A of the Data Center Fire Protection Masterclass. This module focuses on 4 closely connected areas: fuel storage, generator emergency shutdown, IG-100 systems, and foam and water mist protection. The central idea is a decision-focused, listing-controlled design. In other words, we will connect system choices to the conditions they must control, the testing required to verify them, and the processes that support a controlled recovery. The learning path follows the sequence shown here: fuel source, detection, isolation, suppression, and recovery. That sequence is important because fire protection is not a single device or action. It is a coordinated chain, beginning with the hazard and continuing through response and restoration. As we move through the module, we will keep returning to the relationship between fuel risk, generator ESD, water mist, and containment. Together, these concepts provide a framework for evaluating protection around critical data center systems, while keeping attention on control, verification, and recovery. This module focuses on building a complete fire safety and continuity strategy for data center fuel storage and standby generation systems. The scope includes fuel storage, generators, IG-100, foam, and water mist, with attention to both fire protection and operational continuity. The strategy follows 5 connected steps: inventory the hazards, detect problems early, isolate safely, suppress the event, and recover with evidence that systems are ready to return to service. The central goal is to protect generator availability without creating unsafe emergency shutdown logic. We will identify pressurized spray, pool fire, and hot surface hazards, while also coordinating environmental containment and fire response. The audience includes owners and operators, fire and fuel system engineers, generator OEM and controls teams, civil and drainage specialists, commissioning agents, the authority having jurisdiction, or DAMCR, and insurers. By the end, the key deliverables are a fuel hazard register and system architecture, emergency shutdown cause and effect documentation with test scripts, and evidence covering suppression, spill control, and restoration. We will also use common terms such as ESD, UST, FACP, OEM, and IDM throughout the module. This slide introduces the engineering proof arc, the process used to build a complete fire safety and continuity strategy for data center fuel and standby generation systems. The arc moves through 5 connected stages: map the system, engineer the solution, interlock the relevant controls, test the installation, and operate it as intended. The central idea is that engineering proof depends on more than a calculation. A correct hand calculation cannot compensate for a changed enclosure, the wrong component, or a failed field test. Each stage has to remain connected to the conditions that actually exist in the facility. That is why the design proof combines 4 elements: verified inputs, a transparent hand check, the exact listed model, and as-built evidence witnessed in the field. Together, these elements create a traceable chain from assumptions to design decisions, to installed equipment, and finally to demonstrated performance. The goal is not simply to produce a technically correct design on paper. It is to show that the design matches the equipment, the enclosure, the controls, and the operating reality of the data center. This slide introduces Module 10A, Section A, focused on strategy and standards for data center fire protection systems. The central idea is that effective planning begins with a complete inventory of what could influence fire risk and system performance. That means mapping every fuel inventory, every transfer path, every ignition source, and every environmental boundary. The goal is to understand the full system, not just isolated pieces of equipment. The slide organizes that review into 4 connected areas: storage, transfer, engine, and environment. Storage considers where fuel or combustible materials are present. Transfer focuses on how materials, energy, or hazards can move through the facility. Engine identifies the equipment or process that could create an ignition source. Environment captures the surrounding conditions and boundaries that affect the hazard. The learning path moves in a deliberate sequence: authority, hazard, design basis, and acceptance. In other words, we first establish the governing requirements, then identify the hazards, define the design response, and finally determine how that response will be accepted. This framework provides the foundation for the rest of the module. This module focuses on the fire safety strategy for fuel storage, generators, IG-100 systems, foam, and water mist. The central idea is that generator protection has two goals at once: protect people from a developing fire and preserve standby power capability when the facility needs it most. The correct response isolates the fuel hazard without creating an uncontrolled loss of critical power. The response sequence moves from prevention to detection, control, containment, and finally restoration. Prevention addresses leaks, overfills, and ignition sources. Detection must match the hazard, including liquid, heat, flame, and smoke. Control means stopping the fuel feed before the incident escalates, while containment limits spill and contaminated discharge. There are also two important boundaries. The continuity boundary requires proving generator operation, load, and alternate power status before any unload or cool down, and it preserves local manual emergency shutdown authority. The environmental boundary covers spill containment, stormwater or drain isolation where required, and clear responsibility for cleanup and closeout. As we continue, we'll use ESD, UST, FACP, OEM, and IDM as shorthand for emergency shutdown, underground storage tank, fire alarm control panel, original equipment manufacturer, and inspection, testing, and maintenance. This slide maps the main fire and environmental hazards associated with fuel storage and generator systems. The key idea is that the hazard changes as fuel moves through the site, from storage and transfer to the engine, exhaust, batteries, and drainage areas. The fuel system requires controlled filling, suitable tank arrangements, reliable transfer and filtration, and protection against overfill, leaks, and hose connection failures. These safeguards help prevent both fuel release and uncontrolled spread. At the generator package, the most serious scenario is pressurized fuel spraying onto hot engine or exhaust surfaces. Other ignition sources include lube oil, turbochargers, batteries, and electrical equipment. That is why ventilation, physical shielding, local emergency shutdown, and controls against reignition are important. The site environment is part of the protection strategy as well. Bunds, trenches, interceptors, stormwater isolation, and responder access must support containment and emergency response. Any contaminated foam, mist, or firewater also needs a recovery plan. Finally, nearby oil-filled transformers or medium-voltage equipment remain separate fire, drainage, and suppression boundaries. This slide establishes the hierarchy we use when applying standards to fuel storage, generators, IG-100, foam, and water mist systems. The key principle is that requirements must match the specific fuel and generator arrangement, using both the approved additions and the limitations of the listed systems. Local authority requirements come first in practical approval and acceptance. That includes Permen PUPR 26/PRT/M/2008, Local Fire Safety Rules, AHJ or DAMCR access, pre-planning, testing, acceptance, and any environmental, drainage, or emergency plan conditions. The technical standards then define the applicable design framework. NFPA 30 addresses combustible liquids, while NFPA 37 and NFPA 110 cover engines and standby power. Depending on the system, NFPA 11, NFPA 750, NFPA 15, and NFPA 72 may also apply. Finally, the OEM documentation and listing control the details. We need the exact manuals for the generator, tank, fuel system, and controls, along with the listed water mist test protocol for the enclosure and nozzle arrangement. Foam components must also be approved as a complete combination, including concentrate, proportioner, valves, and discharge devices. This slide presents the resilience balancing act during a diesel generator fire or fuel-related incident. The correct response is not simply to shut everything down. It is to isolate the fuel hazard while avoiding an uncontrolled loss of critical power. The objective is controlled isolation with continuity preserved wherever the approved procedure allows. The first boundary is fire safety. Stop the fuel feed before the situation escalates, and unload or cool the equipment only in the sequence that has been approved. The second is continuity. Before any shutdown, prove that the generator is running as expected, confirm its load, and and verify the alternate power state. Local manual emergency shutdown authority must remain available throughout. The third boundary is environmental control. Any spill or contaminated discharge needs to be contained, with stormwater and controlled drains isolated to prevent spread. The equipment identified here is Gen 001 CRIT, a 2,580 kVA diesel generator rated at 1,500 revolutions per minute and currently in standby. Together, these boundaries keep fire response, power resilience, and environmental protection aligned. This section focuses on architecture and design within Module 10A, with an emphasis on coordinating the systems that work together to support fire protection in a data center. That coordination includes tanks, pumps, valves, ventilation, detection, emergency shutdown, or ESD, and approved suppression systems. The goal is not to treat each item as an isolated component, but to understand how the pieces connect and operate as one engineered system. The learning path moves in a practical sequence. Architecture first, then equipment, followed by interfaces and safeguards. The four highlighted design concepts provide a useful starting point for that sequence. Double wall construction addresses the physical arrangement of critical containment. Leak detection provides awareness when an unwanted release may be present. Ventilation supports the management of air movement, while suppression represents the approved means of controlling or extinguishing a fire. Together, these topics establish the design foundation for the rest of the section. The key idea is coordination. Every system must fit into the overall architecture and support the intended safeguards. This module presents the end-to-end fire safety architecture for fuel storage and generator systems. The central idea is that fuel handling, fire detection, emergency shutdown, suppression, ventilation, and containment must operate as one protected system, rather than as isolated functions. The fuel path begins with attended filling and a double-wall tank, supported by interstitial monitoring. High overfill protection stops the fill when needed, while duty and standby transfer equipment and a defined return or overflow route support controlled movement of fuel through the system. The path continues through storage, transfer, the day tank, and the engine. The fire path responds to the specific hazard using appropriate leak, flame, heat, or smoke inputs. Those signals support local, hardwired emergency shutdown, the required ventilation state, and release of the listed foam or water mist system. Finally, the recovery path addresses what happens after an event. Bund and closed drain isolation help contain contaminated liquids, followed by recovery, inspection, functional retesting, environmental closeout, and return to standby. These steps complete the safety cycle. The abbreviations shown here include ESD, UST, FACP, OEM, and ITM. This slide shows the Tier 3 fuel topology, organized as a controlled path from receiving fuel through storage, polishing, transfer, and generation. The central idea is supervised redundancy with independent safeguards and a proven recovery path. Redundancy by itself is not enough if critical functions depend on common equipment. At the tank zone, attended remote filling is paired with an independent high stop. The double-wall underground storage tank uses interstitial monitoring, while normal and emergency vent routes remain unobstructed. Fuel then moves through duty and standby turbine and transfer pumps, duplex filtration, water separation, and a dedicated return. Local HMI controls are backed by hardwired emergency shutdown and valve feedback. At the day tank and generator, the design adds a fire-rated riser, sectional isolation, level and overflow monitoring, leak containment, and an approved safe stop sequence. Finally, fire and environmental controls stay within defined boundaries. Foam water protection in the pump room, leak detection, closed drains, an oil interceptor, and a recovery process that includes fuel quality checks and retesting. These interfaces and command boundaries are what make the system resilient. This slide establishes the fire separation strategy for the Tier 4AB fuel topology. The central principle is independence under a single fire or leak. Each train must retain its own storage, transfer capability, control, routing, and restoration path, without a hidden shared component creating a common mode failure. Train A has a dedicated underground storage tank, fill point, transfer and polishing skid, and distribution route. It also has its own leak zone, local controller, emergency shutdown, and foam package. Train B follows the same logic, with independent storage, pumping, control power, fire-separated routing, and a separate day tank supply boundary and feedback path. The goal is not simply to install two systems, but to prevent one event from disabling both. The validation sequence is equally important. Separate the systems, verify fire-rated barriers and penetrations, monitor the relevant conditions, and prove performance through witnessed network loss, pump fault, leak, and fire scenarios. Finally, changeover and restoration require controlled authority and event logging, so each train can be returned to service independently and with a documented decision trail. This slide compares a Tier 3 centralized arrangement with a Tier 4 topology that separates the A and B trains. On the centralized side, the system is organized around an underground storage tank, a duty pump, a standby pump, duplex filtration, and multiple day tanks. That approach provides backup within a shared structure, but it still depends on common components and paths. The Tier 4 arrangement makes the separation visible. USTA feeds Skid A and Generator A, while USTB feeds Skid B and Generator B. The goal is not simply to add another pump or another tank. It is to preserve independence between the two trains, so one failure does not quietly remove both sides. The most important concept is supervised redundancy, not independent survival. Each train can be monitored and restored separately, with authorization applied independently. Just as important, there must be zero hidden common mode loss. A shared valve or return path could undermine the apparent separation, so those dependencies have to be eliminated or explicitly controlled. This slide focuses on the visual architecture and acceptance basis for underground bulk fuel storage, specifically a double-wall underground storage tank. The central idea is layered protection: the tank envelope, the fill and vent arrangement, and the evidence required before acceptance. The primary safeguard is not a single component, but the combination of secondary containment and continuous interstitial monitoring. The tank itself must be listed, compatible with the fuel, and properly supported through suitable bedding, anchorage, and groundwater considerations. During filling, the process must be attended and include bonding or earthing, a spill container, and an independent high-level shutdown. Normal and emergency venting, including the basis for any flame arrestor, also needs to be established. Acceptance depends on documented proof, not simply installation. That includes factory pressure and leak records, functional tests for the interstice, level detection, and overfill protection, plus as-built evidence for burial, sumps, and leak zones. Together, these controls show that the system is both safely configured and verifiably ready for service. This slide focuses on indoor above-ground fuel storage, specifically a dedicated fuel tank room within a data center. The central principle is that an indoor AST is acceptable only when the entire room is designed as a controlled, fire-protected boundary. That includes fire-rated construction, protected penetrations, mechanical ventilation, appropriately classified electrical equipment, and clear access for occupants and responders. The tank itself needs multiple layers of protection. Secondary containment, such as a double-wall tank, limits the consequences of a leak. Monitoring should include normal level measurement, independent high-level detection, and leak detection. Both normal and emergency vents must terminate in a safe location, rather than exposing the room or nearby equipment to fuel vapor. Finally, protection has to address both fire and environmental impact. The room and tank protection should match the documented hazard basis, while drainage should remain closed and route spills to a sump and oil interceptor. Planning must also account for spill volume and recovery of contaminated water. Together, these measures support emergency shutdown, fire alarm response, and ongoing inspection, testing, and maintenance. This slide compares two fuel storage arrangements: an underground double-wall tank and an indoor above-ground tank. The key point is that tank selection is not based on storage capacity alone. It must reflect the adopted code, site constraints, fire exposure, environmental containment, and long-term maintainability. For an underground tank, burial, groundwater, traffic loads, excavation limits, and remote monitoring become central concerns. Protection typically includes interstitial leak monitoring, sumps, double-wall piping, remote fill, spill control, emergency venting, and reliable inventory management. An indoor above-ground tank is more accessible for service, but it requires a dedicated fire-rated room, controlled access, safe vent termination, secondary containment, and controls that prevent room fire or ventilation problems from isolating the fuel system. In both arrangements, the design must address attended filling, bonding and grounding, overflow prevention, fuel compatibility, polishing, isolation, restoration, and documented testing. Acceptance evidence should include civil and fire barrier records, leak and drain isolation tests, functional alarms and trips, and as left equipment and environmental records. The governing references include NFPA 30, NFPA 110, applicable FM criteria, tank listing requirements, and AHJ, fire authority, and environmental approvals. This slide explains the control chain for fuel transfer, polishing, and leak detection. The key point is that normal transfer and fuel polishing are different operating modes, even though both depend on the same disciplined foundation: valve permissives, leak zone supervision, and a deterministic response when conditions become abnormal. For normal transfer, I first validate the fill conditions: source volume, day tank demand, and available return capacity. I then select one route, prove the valve positions, and allow the duty pump to start only after all permissives are satisfied. The standby pump operates only through approved logic. Polishing uses a dedicated suction and return path, with water and particulate separation. The system should record flow, pressure, differential pressure, and treated volume, while confirming that the fuel chemistry, elastomers, and filters are compatible with the approved blend. If a leak or high condition occurs, the affected pump stops and the selected valves close. A confirmed fire initiates the pump room cause and effect sequence and the specified foam release. Importantly, loss of the HMI or network does not remove local emergency shutdown authority. Defined acronyms support consistent communication during operation, testing, and maintenance. This module focuses on the design method and calculations for fuel storage, generator systems, IG-100, foam, and water mist, with particular attention to fuel quantity, ventilation, and containment. The central requirement is that calculations address normal operation, credible failure, and fire response conditions. For fuel design, we establish the required runtime, usable reserve, and replenishment basis. We also verify the capacity of fill, transfer, return, overflow, and emergency stop systems, while confirming pressure class, material compatibility, and the need for fuel polishing. Ventilation and exhaust design must account for combustion and radiator airflow in every operating mode, as well as heat rejection, exhaust clearances, insulation, and vapor control. In a fire, fans, louvers, and dampers must move to the intended state, with feedback confirming that response. Containment covers bunds, trenches, leak trays, drains, and interceptors, including capacity for contaminated runoff and stormwater isolation. Oil-filled transformers, RMUs, and medium-voltage equipment require a separate containment boundary. Key terms include ESD, or emergency shutdown, UST, FACP, OEM, and ITM. This section focuses on suppression applications, and the central idea is straightforward. The system must match the hazard, not just the room name. That means evaluating the exact enclosure, the fuel scenario, the ventilation state, and the boundary established by the applicable fire test or approval. The selection has to be evidence-based and application-specific. The systems shown here, IG-100, water mist, and SFFF foam, represent different suppression approaches. They should not be treated as interchangeable options. Each one needs to be considered within the conditions for which it is listed, approved, or otherwise demonstrated. The learning path moves through 4 connected questions. First, where is the hazard boundary? Next, how will detection and release logic respond? Then, what hydraulic or agent basis supports the design? Finally, how do we prove that the complete system works as intended? In other words, the goal is not simply to name a suppression agent. It is to connect the application, the design basis, and the integrated proof into one defensible solution. This slide compares 3 suppression packages, each matched to a different fire scenario rather than treated as interchangeable. For a centralized IG-100 system, the primary concern is the generator room or PTU. It uses total flooding with secondary combustion control, and the base case calls for a 41.9% Class C concentration at or below 480 volts. High-pressure water mist is aimed at a containerized generator, where pressurized spray and hot surfaces create a distinctive challenge. The listed approach combines fire-tested enclosure cooling with extinguishment, using at least 128 liters per minute at 100 bar. SFFF foam water addresses a fuel pump room and the risk of a spill or pool fire. Its mechanism is a hydrocarbon blanket supported by closed-drain containment at a 3% concentration and an application density of 0.20 gallons per minute per square foot. The central takeaway is scenario-specific approval. A system approved for one fuel, equipment item, or ventilation condition cannot simply be extended to another. Any change requires new listed evidence. This slide is about selecting the protection method based on the specific fire scenario, rather than treating all generator and fuel hazards the same. The system listing must match the actual hazard, equipment, fuel, enclosure, and ventilation conditions. For a fuel pump room, the example is a hydrocarbon spill or pool fire, addressed with a listed 3% SFFF foam water system. The calculation indicates a 336.5 liter per minute duty, with 250 liters of selected concentrate. A generator enclosure presents a different challenge, involving pressurized spray and hot surfaces, so the example uses listed high-pressure water mist, with a 128 liter per minute duty and 3 cubic meters of usable water. Bulk tanks, day tanks, and dikes require their own listed foam or water spray strategy, including appropriate venting. Oil-filled transformers and medium-voltage boundaries also require separate calculations, fire separation, and drainage. The key design note is that approval for one scenario cannot simply be extended to another. Final selection must follow the applicable NFPA references, the exact FM or listing requirements, and insurer criteria. This slide presents the generator room as a complete, engineered fire protection system, not as a collection of separate components. The protected room requires a fire-rated enclosure with controlled openings, 2-zone detection, and a pre-discharge warning. Fuel and engine status, along with HVAC operation, must be confirmed through feedback before release. At the center is the IG-100 bank, using an engineered 200 or 300 bar cylinder manifold. A selector valve is appropriate only when the system is listed for multi-zone service, and pressure, actuator, and isolation status all need supervision. The discharge path also includes the room nozzles and a pressure relief route. The release sequence is designed to protect people and preserve system performance. Occupied discharge cannot occur until the egress delay is complete. The pressure relief vent and door fan test help verify enclosure behavior, while the design concentration must be maintained for the approved hold time. In practice, this means the room, cylinders, fuel isolation, ventilation shutdown, detection, and controls must work together. The supporting terms include ESD for emergency shutdown, FACP for fire alarm control panel, OEM for original equipment manufacturer, and IDM for inspection, testing, and maintenance. This slide focuses on the controls that make a centralized IG-100 system dependable at the room level. The first requirement is room integrity. Detection is divided into 2 zones, the enclosure is fire-rated, and openings are controlled so the agent can remain effective after release. At the center of the system is the bank of IG-100 cylinders, supported by supervised selector valves. These valves allow one centralized supply to serve multiple protected zones, while also providing monitoring of the valve state and system readiness. The relief path is equally important. Pressure relief vent behavior has been verified through a door fan test, giving confidence that the room can manage the pressure created during discharge without compromising the enclosure. Finally, release is deliberately inhibited until the necessary conditions are proven. Fuel is shut down, CRAC units and fans stop, dampers close, and the approved airflow and opening state is confirmed. The key principle is that discharge occurs only after the room and its connected systems are ready to contain the agent safely and effectively. This slide presents the centralized IG-100 total flooding sequence for a generator room. The key principle is that IG-100 is effective only when the enclosure and the continuing fuel and air energy paths have been driven to the approved release state. The sequence begins with detection in 2 zones, followed by warnings and evacuation. During pre-discharge, the system confirms cross-zone detection or a deliberate manual release, sounds the pre-discharge warning, and starts the approved egress delay. The abort function remains supervised and available only when approved. Next, the release permissives are executed. Selected fuel pumps are stopped, valves are closed and their feedback is proven, and the generator performs its OEM-approved action. Fans, louvers, and dampers are also closed, while the enclosure opening status and pressure relief path are confirmed. After discharge, the system proves release pressure and flow, verifies the alarm chronology, and maintains the agent concentration for the approved hold time. Only then does the process move to ventilation, inspection, recharge, and retesting before the room is returned to standby. These steps coordinate fire detection, fuel isolation, generator control, enclosure integrity, and post-event recovery. This slide focuses on a containerized generator protected by a listed, high-pressure water mist system. The central principle is preserving the exact fire-tested arrangement. That means the enclosure, nozzle locations, potential obstructions, operating zone, ventilation condition, and discharge duration all need to match the tested configuration. The hazard boundary includes the engine, turbocharger, exhaust, and belly or day tank interfaces, along with the doors, louvers, and radiator airflow. The continuing fuel source must also be isolated. On the protection side, use the listed nozzles and a supervised section valve, supported by an accumulator or pump package with verified pressure and flow. Relief, recirculation, and low supply alarms are also part of the package. Acceptance testing then confirms that the installation is faithful and functional. Inspect nozzle locations and obstructions, perform a safe functional release or an approved surrogate test, and prove the pump or accumulator, valve, alarms, and drainage. Together, these checks connect the hot surface zone, radiator airflow, and mist cylinder or pump package into one tested protection system. This slide outlines the water mist architecture for the protected hazard boundary. The boundary includes the engine, turbocharger, exhaust, and belly tank interface, while continuing fuel is isolated. That separation is important because it defines what the system is intended to protect and helps limit the hazard during an event. The package criteria identify the required building blocks of the system: listed nozzles, usable water, drive gas, and a supervised section valve. These elements work together to provide a controlled and monitorable means of delivering water mist to the designated section. The emphasis here is not simply on having suppression equipment in place, but on ensuring that the complete package is available and supervised. The acceptance check then focuses on practical access and containment. Nozzle access must remain clear, so the equipment can be inspected and maintained. Any water or fuel discharge must also be captured within approved drainage. The key acceptance principle is that protection must be both deployable and safely managed after discharge. This slide presents a containerized fuel pump room as a complete, packaged fire protection application. The important concept is that the enclosure, pump skids, ventilation controls, leak detection, fire alarm panel, foam equipment, and closed drainage are commissioned together, rather than treated as separate installations. The enclosure includes a fire-rated container, supervised louvers and dampers, duty and standby transfer equipment, polishing components, zoned leak cable, and local emergency shutdown. The foam release package includes a compatible SFFF concentrate, bladder tank, proportioner, approved discharge devices, and the defined simultaneous operating area. Release sequencing also includes a pre-discharge warning, along with manual release and abort functions where approved. The final section focuses on integrated proof testing. That means verifying pump and valve shutdown, position feedback, foam valve operation, pressure switch response, and the expected alarm chronology. It also means confirming drain isolation, recovery, and complete restoration to the as-left condition. In short, protection is demonstrated as one coordinated system, not simply as a collection of installed components. This slide describes the architecture of the SFFF foam water system by connecting the hazard, the system components, and the containment loop. The hazard begins with the equipment and materials that need protection: transfer pumps, filters, and pressurized fuel. These conditions create the need for a controlled foam water solution rather than relying on water alone. The system uses 3% SFFF concentrate, supplied through a listed bladder tank and mixed by a proportioner. Together, these components provide the intended foam water mixture for discharge. The containment loop is equally important because the discharged mixture may carry recovered fuel and foam solution. Before any discharge occurs, the drains must isolate. That allows the fuel and foam water mixture to be directed into the 9.0 cubic meter closed recovery tank, rather than leaving the protected area through the drainage system. So, the key idea is that protection and containment work as one architecture. The system delivers the agent, while the loop controls what happens afterward. This slide introduces Section D, Focused Design Calculations, within Module 10A. The purpose is not to perform every possible calculation or reproduce an entire equipment listing. Instead, we retain the hand checks that directly determine duty, quantity, containment, or acceptance. Those checks provide a practical bridge between the design intent and the final, exact listed model selected with the original equipment manufacturer. The section brings together 4 application areas: water mist IG-100, SFFF foam, and integrated proof. Each represents a different part of the fire protection system, but the same discipline sequence applies across them. First, verify the boundary. Then complete the hand check that is genuinely useful for the decision being made. After that, confirm the exact listed model, and finally demonstrate performance through witnessed field proof. The key idea is that focused calculations support verification. They do not replace the final listing or the OEM model. This approach keeps the work technically defensible, easier to review, and aligned with what must ultimately be accepted in the field. This slide presents the calculation roadmap for the data center fire protection system. The goal is not simply to produce a number, but to maintain one auditable chain from the original survey through final acceptance evidence. We begin by surveying the protected space and freezing the geometry. Then we classify the hazard and its operating state, calculate the required flow or quantity, and select the package, including the necessary reserve. The design is verified through hydraulic checks and room-level review, and finally accepted through witness testing and recorded evidence. The central engineering relationship is that design proof depends on 4 connected elements: verified inputs, a transparent hand calculation, the exact listed model being used, and as-built evidence witnessed in the field. The key decision is to use one frozen boundary for every formula, drawing, cause and effect record, and test script. Any discrepancy must be resolved before approval, rather than carried forward. The governing references listed here are NFPA 750, NFPA 11, NFPA 2001, and the applicable FM standards. This slide establishes the calculation basis for selecting and applying a fire protection design. The key idea is that the authority hierarchy prevents incompatible components and assumptions from being combined. We begin with the AHJ, or authority having jurisdiction, then apply the adopted standard, the owner or insurer requirements, and finally the exact listed system. The requirements differ by technology. For water mist, NFPA 750 and FM data sheet 4-2 apply, and the fire test envelope governs. There is no universal generator enclosure density. For IG-100, NFPA 2001, ISO 14520, and the applicable FM concentration basis must be used with the exact listed cylinders, valves, piping, and nozzles. SFFF foam requires a compatible, approved set of concentrate, proportioner, and devices. Battery and Tier 4 applications add separate thermal runaway evidence, with reserve and restoration tied to mission risk. The engineering decision is straightforward. Apply the most stringent applicable requirement, without mixing concentrations, hydraulic data, nozzles, foam components, or software from different approvals. The governing references include the listed NFPA standards, ISO 14520, FM datasheets, and the AHJ. This calculation establishes the geometric basis for three distinct protected envelopes: the generator container, the PTU container, and the fuel container. The drawing matrix compares their dimensions, floor areas, gross volumes, and principal hazards, so each space can be evaluated for the appropriate fire protection system. The generator container is the largest, at 56.10 square meters of floor area and 199.155 cubic meters of gross volume. Its primary hazard is the engine together with the 16,000-liter belly tank. The PTU container is smaller, but it combines low-voltage equipment, ATS and UPS assemblies, and a lithium-ion battery. The fuel container is the most compact, with transfer and diesel polishing equipment as its principal hazard. The key design point is that external geometry is not automatically the protected net volume. Internal clear dimensions, partitions, solid obstructions, and openings must be reconciled separately before final calculations. These values are therefore a preliminary envelope and nozzle or spill area basis, while gross volume supports listing and agent boundary review. Final construction must follow the supplied generator, PTU, and Tier 4 fuel container drawings, with the exact approved shop drawings governing. This slide establishes the calculation basis for the three protection system examples. The central rule is simple. The selected result is the calculated duty, rounded up to the next approved equipment size. That means we show the engineering calculation clearly, while preserving the listing gate. The assumptions are not hidden. They are visible, testable, and intended to be replaced with approved vendor data before IFC issue or acceptance. For the environment, the training basis uses temperatures from 20 to 40 degrees Celsius, an altitude of 8 meters, and an altitude factor of 1.000. The water mist case assumes 8 liters per minute per nozzle at 100 bar for a 20-minute limited drainage scenario, while recognizing that the exact fire test nozzle and duration remain controlling. The IG-100 example uses an 80-liter, 200-bar cylinder, with the stated mass and volume cross-checked to the enclosed sheet. The foam screen uses 3% SFFF, a flow density of 0.20 gallons per minute per square foot, full floor coverage, and 20 minutes. Importantly, minimum device pressure may govern above density flow. These assumptions are tied to the listed NFPA and FM references. This slide defines when a protection system calculation can be considered complete. The key point is that calculation quality closes only when field conditions match the approved model. That means the inputs must be frozen at their approved values, the calculation must be checked by hand, the output must match the exact listed or OEM result, and the as-built test must be witnessed and documented. There are 4 areas to control. First, drawing inputs. Verify dimensions, equipment, openings, internal clearances, and permanent solids, all under revision control. Second, system inputs. Confirm the approved nozzles, cylinders, foam components, and approval schedule. Substitutions require recalculation. Third, operating state. Fuel, fans, dampers, and electrical conditions must reflect the intended release state, with feedback proven. Finally, preserve the evidence, including FAT and SAT records, flow and enclosure tests, integrated systems testing, certificates, plots, calculations, and a clear chronology. The engineering decision is straightforward. Resolve every mismatch before handover. A correct calculation cannot compensate for a changed enclosure, an incorrect component, or a failed field test. These decisions should be aligned with the governing NFPA, FM, and listed DITM references. This slide shows the first calculation step for the water mist application, establishing the enclosure geometry. The drawing gives an overall length of 16.50 meters and a width of 3.40 meters. Multiplying those values produces a gross floor area of 56.10 square meters. Using the enclosure height of 3.55 meters, the gross geometric volume is 199.155 cubic meters. These calculations confirm the listed boundary, including the radiator and intake extensions in the external envelope. However, they are only a screening step. The internal clear width still needs to be checked during the final listing review, and the final fire test boundary must use verified internal geometry. The key engineering decision is that 155 cubic meters is not a nozzle count calculation. It is used to screen the exact fire-tested application. Nozzle quantity, spacing, openings, and obstructions must come from the approved listing, supported by the supplied generator drawing and the governing references, including NFPA 750, FM Datasheet 4-2, and the exact approval guide listing. This slide calculates the fuel run-on volume that links emergency shutdown timing to containment needs. The governing relationship is straightforward. Spill volume equals fuel flow multiplied by the confirmed isolation time, plus any drainable inventory trapped downstream of the valve. In this project scenario, the run-on contribution is 300 liters per minute over 5 seconds, which produces 25 liters. The downstream filters, hoses, and local piping add another 75 liters, bringing the calculated spill to 100 liters. The approved design scenario is 50 cubic meters or 500 liters for machinery enclosure recovery. That value must be supported by the pump curve and approved cause and effect inputs, then proven during site acceptance and integrated system testing. The calculation also reflects the hazard, not just the volume. Hot turbocharger, exhaust, and manifold surfaces create an auto-ignition concern, while local shadowing and possible reignition require evaluation. Finally, this scenario is separate from containment for a full 16,000-liter belly tank rupture, which must be checked independently using the supplied generator information, FMDS 7-32, and the exact water mist listing. This step converts the approved nozzle layout into the simultaneous water mist flow demand. The governing calculation is the sum of each nozzle's discharge coefficient multiplied by the square root of its operating pressure. Using 16 nozzles, a K factor of 0.80, and 100 bar, the result is 128 liters per minute. The hand check also shows where that demand comes from. The overhead portion is 12 nozzles at 8 liters per minute, or 96 liters per minute. The supplemental portion adds 4 more nozzles at 8 liters per minute, contributing 32 liters per minute. Together, those two approved fire test layout components total 128 liters per minute. For final hydraulics, I would use every nozzle's exact K factor and calculated pressure rather than relying only on this summary check. The selected package duty is the next listed rating, 150 liters per minute, providing 22 liters per minute above the calculated demand. The engineering decision is to carry the same listing-based operating zone through the OEM hydraulic model, package selection, usable water check, and field test, in accordance with NFPA 750 and the applicable manufacturer calculation. This calculation establishes the minimum pressure required at the source for the hydraulically remote nozzle. The governing relationship is straightforward. Source pressure must cover the nozzle requirement, pipe and fitting losses, device losses, and elevation head. The nozzle requires 100 bar at minimum. The main and remote branch contribute 3.68 bar of pipe loss. Filters, valves, controls, and static rise add another 12.35 bar, made up of 12.00 bar for devices and 0.35 bar for elevation. Adding those values gives a minimum source pressure of 116.03 bar. That number is the hydraulic threshold, not automatically the equipment selection. The recommended engineering decision is to select a listed package rated for 150 liters per minute at 125 bar duty, providing margin above the calculated minimum. However, the package must still pass the exact as-built route and remote nozzle limits using its certified pump curve and the OEM hydraulic model. The final design should also confirm the relief setting, recirculation arrangement, and nozzle limits, with NFPA 750:2023 serving as the governing reference. This slide shows how we calculate both usable water storage and containment capacity for the water mist system. The starting point is the simultaneous flow rate of 128 liters per minute and an approved duration of 20 minutes, giving a discharged volume of 2,560 liters. We then apply the documented 10% project allowance. That increases the required usable water supply to 2,816 liters, so the selection is rounded up to 3.0 cubic meters. At that storage volume, the available duration is about 23.44 minutes, which exceeds the adopted 20-minute screening value. Containment is calculated separately, combining the 2.56 cubic meters of discharged water with the approved 0.50 cubic meter spill, then applying the same allowance, produces 3.37 cubic meters, leading to a 3.5 cubic meter selection. The engineering decision is that the worked pump and tank option passes the 20-minute requirement. Any cylinder-based package must still demonstrate the same usable water and drive gas capacity at 128 liters per minute. These checks follow the governing FM and NFPA criteria, along with the package's actual usable volume data. This slide calculates the net protected volume for two separate areas in the IG-100 system. The governing formula is straightforward. Net volume equals the clear compartment volume minus sealed, permanent, impermeable solid displacement. That means we deduct equipment that physically and permanently occupies space, but not air-filled voids or communicating service spaces. For the electrical zone, the clear volume is 117.00 cubic meters. We subtract 15.00 cubic meters for the UPS, switchboards, and CRAC solids, leaving a net protected volume of 102.00 cubic meters. The communicating cable and service air volume remain included. For the battery zone, 31.50 cubic meters is reduced by 6.00 cubic meters for cabinets and cooling equipment, resulting in 25.50 cubic meters. Battery rack voids that contain air are not deducted, and this area remains a separate selector and quantity zone. The engineering decision is to freeze these two values for the worked example, then repeat the survey after any equipment, partition, or cable change. The calculation is governed by NFPA 2001, ISO 14520, and the exact as-built survey. This slide establishes the calculation basis for the IG-100 design concentration. The governing formula is to adopt the greatest applicable value among Class A, the energized Class C voltage basis, and the AHJ or listing requirement. For the base case, 41, 9% applies only after the release state voltage and energization matrix has been signed. The main low-voltage system is rated at 415 volts AC, which supports the Class C reference for energized equipment at or below 480 volts. However, that input label does not establish the voltage of the UPS internal DC link, or the battery string. Those values require confirmation from the equipment vendor or OEM, because the internal DC link may exceed 480 volts. Isolation and stored energy are separate engineering questions. If every energized source is proven to be 480 volts or less, the calculation can use 41.9%. Otherwise, the design must address the greater than 480 volt sensitivity, or the equipment must be de-energized. The IFC calculation must include a signed voltage and energization matrix from the UPS and battery vendors, supported by FMDS 4-9, NFPA 2001:2025, nameplates, and one-line diagrams. This calculation establishes an important limit for the role of IG-100 in a battery zone. IG-100 can provide supplementary control for secondary Class A and Class C fires, and it leaves no residue while remaining electrically non-conductive. However, IG-100 alone cannot terminate the internal reactions of a lithium cell thermal runaway, because those reactions are self-heating and not dependent on the surrounding oxygen level. That means the battery strategy must be layered. It should include early off-gas detection, BMS isolation, and propagation controls that have been tested and documented. The required evidence includes UL 9540A or equivalent OEM propagation data, along with project-specific confirmation of rack spacing, cooling, isolation, and emergency response. Additional controls may include ventilation or deflagration protection, and water-based or manual response may still be necessary. So the engineering decision is to retain the IG-100 calculation only as secondary fire protection, and label that limitation clearly in both the cause and effect documentation and the emergency plan. The governing references are NFPA 855:2026, FMDS 5-33, and the applicable battery and UPS manufacturer hazard documentation. This slide walks through the IG-100 mass calculation in 4 steps. First is the concentration gate. The base case design concentration of 41.9% applies only when every energized source has been proven to be 480 volts or less. That condition determines whether this pathway can be used. Next, the required mass is calculated using the stated formula: net volume divided by the minimum specific volume, multiplied by the logarithmic concentration term and the altitude factor. For this case, the inputs are a net volume of 102 cubic meters, an S-min value of 0.858300 cubic meters per kilogram at 20 degrees Celsius, and a log term of 0.543005. These values produce a required mass of 64.53 kilograms. The final step is cylinder rounding. Dividing 64.53 kilograms by 17.9 kilograms per cylinder gives 3.6, so the design must round up to 4 cylinders, not 3. The verification check confirms that 4 cylinders produce a 45.26% achieved concentration at 20 degrees Celsius, which exceeds the 41.9% target and therefore passes the check. This slide covers the cylinder count calculation for the IG-100 system. The governing rule is simple: round the required agent mass up to the next whole cylinder. The formula divides the calculated mass by the certified usable mass per cylinder, then applies roundup. For the electrical actuation case, the requirement is 64.53 kilograms. Each listed 80-liter, 200-bar cylinder provides 17.9 kilograms of usable agent, so the calculation is roundup of 64.53 divided by 17.9, resulting in 4 cylinders. That delivers 71.6 kilograms in total. The battery actuation case is much smaller. Its requirement is 16.13 kilograms, which still rounds up to 1 complete cylinder, delivering 17.9 kilograms. The important point is that the exact listed usable content and fill tolerance must be used, rather than an assumed value. Control is equally important. Cylinder groups must be individually supervised, with a listed staged release arrangement. We cannot allow an uncontrolled 4-cylinder discharge into the smaller battery zone. The engineering decision is therefore to use only a listed selector and staged cylinder configuration that demonstrates the intended count for each compartment, consistent with NFPA 2001, FMDS 4-9, and the applicable equipment listing. This slide documents the concentration calculation for the selected IG-100 cylinder quantities. The governing formula determines the achieved concentration, C of T, as a function of temperature, the specific volume of IG-100, the number of selected cylinders, and the net protected volume. For the electrical zone, the selection is 71.6 kilograms for 102 cubic meters, producing 45.255% at 20 degrees Celsius. The battery zone uses 17.9 kilograms for 25.5 cubic meters, which intentionally preserves the same mass-to-volume ratio and therefore the same concentration result. At the maximum temperature considered, the electrical zone concentration rises to 47.460%. The key compliance check is the minimum concentration. 45.255% is greater than or equal to the required 41.9%, giving a 3.355 percentage point margin after rounding. That check passes. The maximum condition still requires an exposure review, because normally unoccupied discharge assumptions and the applicable safety limits govern. Overall, the engineering decision is that the selected quantity passes the concentration check, using the corrected fill basis rather than the earlier volume shortcut. This slide clarifies how to calculate the IG-100 cylinder quantity, and the key point is that reserve is an approved continuity choice, not an automatic tier requirement. The duty bank is sized for the maximum single-zone demand. In this example, that means 4 operating cylinders, with the battery release using 1 supervised duty cylinder. A second set of 4 cylinders is added only when the owner or insurer's approved continuity basis requires a full 100% reserve. If that reserve is selected, the installed total becomes 8 cylinders at 17.9 kilograms each, or 143.2 kilograms. Without the reserve, the duty bank alone is 71.6 kilograms. Restoration also matters. After an event, the system may be switched to reserve through a controlled, supervised selector changeover, but only after inspection. The discharged bank must then be recharged and independently reproved. So, in the engineering documentation, duty and reserve should be shown separately. A tier label by itself does not create a reserve quantity, and reserve does not eliminate the need for investigation, inspection, or retesting under the governing standards and the project restoration plan. This slide shows how we calculate the required vent-free area for an IG-100 system. The key point is that vent sizing depends on 2 things: the OEM's peak discharge flow and the enclosure's allowable structural pressure. Free area is not the same as the nominal size of a grill. The calculation uses peak volumetric inflow, discharge coefficient, allowable pressure, and air density, with a documented project allowance of 1.15. For this design, the inputs are a discharge coefficient of 0.65, an allowable pressure of 250 pascals, and an air density of 1.20 kilograms per cubic meter. The electrical zone has a peak flow of 0.70 cubic meters per second, producing a calculated area of 0.0607 square meters. The selected listed bidirectional vent therefore needs at least 0.065 square meters of effective free area. The battery zone requires less. Its 0.18 cubic meter per second peak flow produces 0.0156 square meters, so the selected vent must provide at least 0.020 square meters. Before finalizing, we still need to account for opening time, duct or louver losses, and dynamic verification. We also need to confirm wall, door, and ceiling limits, and keep the vent path outside occupied egress routes. This slide defines how we make the room integrity decision for an IG-100 system. Door fan acceptance is based on measured leakage, combined with an approved integrity model, rather than a simplified constant leakage assumption. Pass means the model predicts concentration at or above Cmin throughout the required hold time. Cmin is the minimum concentration required at the end of that period, and both the threshold and duration must come from the adopted design or listing, not from a universal rule. The calculation requires the initial concentration, Cmin, hold time, measured equivalent leakage area, and the leakage distribution. The electrical or UPS zone and the battery zone must be evaluated separately, in the exact release state enclosures. Each compartment needs its own test and report, with the approved model result clearly documented. Separate functional checks also cover vents, dampers, alarms, and noise. These equipment reviews should not be confused with proof of agent hold time. The engineering decision is to accept only the calibrated door fan test, approved model, vent and damper testing, and controlled restoration, following the governing references, including NFPA 2001, FMDS 4-9, and listed system data. This slide shows how we calculate the credible fuel release for the containment design. The key point is that the run-on test evaluates the ESD response and establishes the spill scenario, not the foam density. The calculation is straightforward. Pump flow multiplied by confirmed stop and valve closure time, divided by 60, then added to the drainable inventory trap downstream. For this worked example, the assumed pump flow is 300 liters per minute, and the confirmed isolation time is 5 seconds. That gives 25 liters of pumped run-on. Adding the 75 liters retained in the downstream line and filter produces a calculated release of 100 liters. However, the adopted containment design spill is more conservative, 1.00 cubic meter. This is an approved project risk scenario, not a standard multiplier. We should use that value for the worked credible spill case, while separately checking larger pipe rupture scenarios or an operator filling scenario. The pump curve, control set point, and hardwired feedback should be confirmed during SAT and IST. The governing basis includes FMDS 7-32, the fuel PNID and pump data, and the cause and effect documentation. This slide establishes the governing hazard area for the SFFF foam calculation. The key decision is to use the largest connected spill footprint, rather than limiting the analysis to the local equipment trays. The tray and pump and skid footprints represent approximately 12 square meters, and they may help collect a leak, but they do not capture every possible pipe or valve failure. Because the fuel can migrate through shared container drainage and across the connected floor, the adopted area is the full internal floor area, 746 square meters. In formula terms, the hazard area is the maximum of the tray area and the connected spill area, which here equals the floor area. That selected value is carried through the density, nozzle, foam solution, concentrate, and containment calculations. For the listed flow density example, the area is converted to approximately 320.184 square feet by multiplying by 10.7639. The governing references are NFPA 11:2024 and FMDS 7-32, together with the approved nozzle coverage and drainage layout. This slide determines the governing flow for the SFFF foam system. Two checks are compared: the density-based demand and the demand from 6 simultaneously open devices. The device calculation is 6 times 14.816, which produces 88.897 gallons per minute. That is higher than the 64.037 gallons per minute density result, so the device flow governs. The calculated solution demand is 336,513 liters per minute. The conversion from gallons per minute uses a factor of 3.7854, giving that metric total. When this flow is divided across the full floor area, the resulting actual density is 0.2776 gallons per minute per square foot, or 11.31 liters per minute per square meter. That value describes the achieved flow density, but the governing basis remains the larger device demand. For engineering use, 336.513 liters per minute is carried into the pipe, proportioner, and storage calculations. The selected package rating is the next listed duty, 400 liters per minute, providing capacity above the calculated demand. This decision follows NFPA 11:2024, the listed minimum device pressure, and the exact hydraulic calculation. This slide shows how the minimum package pressure is established for the foam system. The governing relationship is that supply pressure must cover the remote device requirement, distribution losses, valve and proportioner losses, elevation, and the documented design margin. At the most remote open device, the minimum requirement is 7 psi, or 0.483 bar. Pipe and fitting losses contribute another 1.31 bar. The valve and proportioner add 2.00 bar, while the elevation allowance adds 0.30 bar. Finally, the design margin is 0.70 bar. Together, those values produce a required pressure of 4.79 bar, so the selected package is rounded up to 50 bar. This is a coordinated network hand check, not a substitute for the exact approved models and loss curves. The example proportioner range is 250 to 1,000 liters per minute, and the 336.5 liters per minute point passes that range. The engineering decision is therefore to select a listed 400 liter per minute package at 5.0 bar, then verify proportioning accuracy at minimum, design, and maximum flow. The governing reference is NFPA 11:2024, along with the approved device data. This slide calculates the foam solution and concentrate quantities for one discharge. The governing hydraulic flow is 336.513 liters per minute, and the approved duration is 20 minutes. Multiplying those values gives 6,730, 3 liters of total foam solution. The concentrate fraction is 3%, so the usable concentrate requirement is 6,730.3 multiplied by 0.03, or 201.9 liters. The remaining 97% is the water portion, which equals 6,528.3 liters. Keeping these quantities separate is important because the site firewater supply remains independently available. The proportioning check divides 201.9 liters of concentrate by 6,730.3 liters of total solution, confirming a 3% target. The applicable acceptance band still needs to follow the exact listing for the concentrate and proportioner. The engineering decision is therefore to size storage from the actual 6-device hydraulic flow, rather than from the lower density-only flow. This calculation is governed by NFPA 11, the 2024 edition, FMDS 7-32, and the exact equipment listing. This calculation establishes the recovery volume needed for the SFFF foam system, based on the solution discharge, a credible fuel spill, and the documented project allowance. The selected pump duty is 400 liters per minute at 5 bar, and the 20-minute hydraulic demand produces 6.730 cubic meters of solution discharge. The adopted fuel spill scenario adds another 1.000 cubic meters. Applying the formula, containment volume equals the combined discharge and spill volume, multiplied by 1.10. That gives 8.503 cubic meters. So the design decision is to select a 9.0 cubic meter recovery capacity. This is also equivalent to an approximately 303 mm depth if spread across the full floor area. The key requirement is not simply storage volume. The recovery route must be closed, or provide equivalent approved containment, and must prevent fuel or foam water from migrating into other compartments. Larger rupture or filling events are outside this adopted scenario and require separate analysis. The decision is governed by NFPA 11:2024, FMDS 7-32 containment and water supply criteria, and the environmental plan. This calculation slide defines what acceptance means for the SFFF foam system. Acceptance is not a single flow test. It proves the complete release, proportioning, recovery, and integrated control chain. The system passes only when every listed function operates together at the as-built operating point. The release sequence must be demonstrated through either 2 heat zones or an approved manual release, using the project-specific delay. Warning, abort, fire panel logic, fuel and ventilation shutdown, closure limits, and feedback must all respond as approved. If a permissive fails, release must be inhibited or the system must alarm, according to the approved design. Hydraulic performance is verified at 336.5 liters per minute, with at least 7 psi at the remote point. A test manifold and calibrated instruments record the result against the pass target. Proportioning must achieve 3% within the exact listed tolerance, using a contained test. Finally, the valves, concentrate, drains, and alarm states must be restored. This integrated acceptance approach is governed by the listed NFPA, FM, and project-specific procedures. The key point is that no isolated result can substitute for synchronized cause and effect proof. This slide brings the 3 suppression approaches together in one final engineering comparison: generator water mist, PTU IG-100, and fuel container SFFF. The calculated duty for water mist is 128 liters per minute, with a minimum pressure of 116.03 bar. The selected package is slightly higher, at 150 liters per minute and 125 bar, with a 45 kilowatt pump. It includes 4 duty cylinders, plus 4 reserve cylinders if approved, and stores 3 cubic meters of usable water. For the PTU IG-100 system, the calculated requirement is 64.53 kilograms, with an additional 16.13 kilograms shown in the comparison. The selected basis is 4 duty cylinders and 4 reserve cylinders, subject to approval. Its primary proof is concentration, ventilation, and required hold time. The fuel container SFFF case requires 336.5 liters per minute at a minimum of 4.79 bar. The selected package provides 400 liters per minute at 5 bar, with at least 201.9 liters usable and 250 liters selected for duty. The key engineering rule is to round only to approved equipment and never mix assumptions across listing families. Each system must be validated against its own pressure, duration, concentration, and proportioning requirements. This slide presents the acceptance evidence matrix for 3 fire protection approaches: water mist, IG-100, and SFFF foam. The key point is that acceptance evidence is system-specific, but it follows one controlled commissioning structure. The process begins with design review. For water mist, that means confirming the fire test envelope and hydraulics. For IG-100, it includes protected volume, concentration, and venting. For SFFF foam, the review covers density, devices, and proportioning equipment. Factory acceptance testing then verifies the packaged equipment, while site acceptance testing confirms installed performance, including pressure, flow, interlocks, release circuits, and concentration-related functions. Finally, integrated systems testing and restoration demonstrate operational sequences, such as fuel shutdowns, dampers, alarms, emergency shutdown, drainage, and reserve changeover. Ownership also changes by stage, moving from the designer and authorities having jurisdiction to manufacturers, commissioning agents, installers, and owner operations. One important control is that a safe surrogate may replace a destructive discharge only when the approved procedure proves the same functional and measured acceptance objective. The governing references include the listed NFPA standards, FM guidance, and exact OEM acceptance manuals. This slide defines the command boundaries between the generator, fuel system, fire systems, and monitoring platforms. The core operating sequence is sense, alarm, decide, act, and confirm feedback. A fire signal must reach the correct local controller and operator directly, rather than depending on one monitoring server. The generator controller provides running, stopped, load, cooldown, and fault status. It performs only the approved safe stop sequence, then returns hardwired confirmation. Fuel controls can stop transfer, close selected valves, and supervise day tank alarms. Importantly, local manual isolation remains available if the network or HMI is unavailable. The fire alarm system processes leak, heat, flame, and smoke inputs, along with suppression status. The FACP or FCC preserves the chronology of alarms, releases, supervisory conditions, and troubles. BMS, EPMS, and the SOC provide status, trends, and operating context, but they are monitor only unless a command interface has been specifically approved and tested. The principle is simple. Local systems act safely, while supervisory systems display and coordinate within clearly tested limits. This slide explains the cause and effect logic for fuel emergency shutdown and suppression. The matrix separates 4 conditions that must not be treated as interchangeable: a leak, a confirmed fire, a deliberate manual ESD, and a suppression release. The key principle is that a leak alarm does not automatically become a fire release command. For a leak, the system should alarm locally and at the approved control room, stop the affected transfer, and close the relevant valve. Feedback must then prove that the action occurred. For a confirmed fire or an authorized manual ESD, the response may escalate. If approved and time permits, alternate power or unload actions can be used. A confirmed fire may require immediate fuel isolation along with the listed suppression system, such as IG-100, foam, or water mist. After an event, reset is governed, not automatic. The engine, tank, piping, ventilation, and containment need inspection. Reset requires named authorization, followed by reproving normal and fault states before the system is returned to standby. This sequence preserves clear decisions, verified feedback, and controlled restoration. This slide organizes the main failure modes into 3 connected areas: fuel, protection, and containment. The key idea is to design for faults that can feed, hide, or spread a fuel fire. Fuel faults can begin with a stuck-open valve, a pump contactor, or a failed non-return valve. They can also involve an overfilled day tank, a blocked return or overflow path, a false level indication, or a failure in a hose, seal, filter, or pressure relief device. Protection can fail as well. A detector may be blind or contaminated, or lose power, circuitry, or network connectivity. Mist nozzles may be blocked, damaged, or mispositioned, and foam protection can be undermined by the wrong concentrate, incorrect proportioning, or an empty supply. Finally, containment must be treated as part of the fire strategy. Open drains, failed isolation, bypassed interceptors, bund penetration, inadequate capacity, or blocked access can allow fuel or contaminated runoff to spread. That runoff also needs a defined recovery or waste route. These safeguards should be verified through ESD, the FACP, OEM requirements, and disciplined ITM. This slide presents the cause and effect interlock matrix for the fire protection system. It maps initiating conditions on the left, such as a leak, a fill spill, a confirmed cross-zone fire, or a manual emergency shutdown, against the affected system states across the top. Those states include fuel transfer, ventilation, suppression, generator operation, and drain status. The key point is that each event produces a defined, controlled response rather than a single, generalized shutdown. For a fill spill, the system stops filling at the source, isolates the controlled drain, and generates an alarm. Suppression is released only when the approved fire criterion is met. For a confirmed fire, the identified fuel path and generator are stopped as approved, while suppression remains a separate, supervised action. A manual ESD stops the affected pump and closes the valve, but it does not release suppression. Hardwired local ESD authority remains available even if the HMI or network is lost. This separation helps prevent unintended agent release while preserving immediate local control. This module moves into Section E, which focuses on scenarios and the interfaces between fire protection, standby power, and environmental containment. The objective is to test whether credible events can be managed without destabilizing those supporting systems. The central learning path is: initiate the event, isolate energy, suppress or contain the hazard, prove that the response worked, and then restore the system. The scenarios shown here provide 4 practical contexts for that sequence. A fill spill tests how a release is identified and contained. An engine spray scenario examines the response to a potentially hazardous spray event. A container fire shifts attention to fire control and the interaction with surrounding protection measures. Finally, recovery addresses the steps needed to return the facility and its systems to a stable operating condition. These are not isolated exercises. They are interfaces that need to work together, from the initial initiating event through restoration, while maintaining both power resilience and environmental control. This section uses those scenarios to make the response process concrete and testable. This scenario focuses on a pressurized fuel spray while the generator is still running. The objective is twofold: protect life immediately and contain the event while coordinating a controlled shutdown whenever conditions allow. The sequence is detect and confirm, alarm and assess, establish an alternate load path if approved, then manage fuel, ventilation, suppression, and verification. First, confirm flame or heat, and identify the engine's running and load status. At the same time, check fuel pressure, leak conditions, day tank status, and ventilation. Manual emergency shutdown must remain available throughout the response. If time and procedures permit, transfer or unload the load using the approved path, then follow the OEM shutdown and cooldown process. If the fire matrix requires immediate isolation, that priority takes precedence. For the fire action, stop fuel transfer, close the selected valves, and prove their position. Set ventilation to the designated fire mode, and release water mist only within the approved enclosure and under the specified criterion. Recovery is not complete until time-synchronized records confirm valve, pump, fan, alarm, release, and generator actions. Finally, inspect, replenish, retest, and authorize environmental and standby restoration separately. This timeline shows how the system maintains continuity when a spray fire is detected in a running generator. The sequence begins at T=0, when both flame sensors trigger and the engine running state is confirmed. That confirmation starts the response without relying on a single signal. In Phase 2, The system addresses the critical wait and transfer period. Alternate power may be established, or an OEM-approved cooldown may be used, but only when approved and when the available time permits. The transfer window can vary, with a reference limit of up to 90 seconds. Phase 3 is the hardwired stop transfer step. The fuel valve is commanded closed, the dampers are expected to shut within 10 seconds, and the emergency shutdown interlock becomes active. Phase 4 then releases water mist while synchronized records capture activation, flow, and isolation status. The system also verifies that isolation has occurred before agent discharge is confirmed. Finally, recovery is deliberately controlled. Environmental and standby restoration require separate authorization, followed by the restoration sequence, standby confirmation, and a manual reset. The key principle is staged action, verified by both equipment status and recorded evidence. This scenario focuses on a spill during remote fuel filling, where the immediate priorities are to prevent escalation to a pool fire and keep contaminated liquid out of storm drainage. The response follows 5 actions. Stop the fill, raise the alarm, contain the spill, protect people and equipment, and recover the liquid. The most important prevention measure is attended filling with reliable two-way communication. Before transfer begins, confirm available tank volume, inspect the hose and connection, apply approved bonding and earthing, and verify that an independent high overfill stop is available. If a spill occurs, stop transfer at the source, isolate the fill point, remove ignition sources, and notify the control room and response team. Keep the release inside the controlled area. Close drainage isolation before product can reach stormwater, deploy compatible spill control materials, recover the liquid, notify the environmental owner, and preserve evidence. Closeout includes cleaning surfaces, disposing of contaminated materials, inspecting the hose and tank, investigating the cause and testing levels, alarms, valves, and shutdown functions. Environmental approval is required before reopening. This slide shows the remote fill spill containment loop, and the key idea is that each step moves the incident away from uncontrolled discharge and toward recovery. Product enters at the fuel inlet and fill point at a flow of 200 gallons per minute, then moves toward the catch basin. If a spill occurs, the isolation valve closes before product can reach the storm drain network. From there, the material is directed into a containment tank, where the spill remains confined. The sequence is stop, alarm, contain, recover, and close out. First, attended filling triggers an independent high stop. The source is isolated, and ignition sources are removed. Next, the drainage valve shuts before product reaches stormwater. Contaminated liquid is then physically recovered from the control area. Reopening is not automatic. The hose and tank must be inspected, and environmental closeout must be approved before filling resumes. The containment tank is identified with a 5,000-gallon capacity, providing a defined destination for the spill rather than allowing it to spread through the drainage system. This scenario covers a confirmed fire in a containerized fuel pump room. The response follows a controlled sequence. Detect the fire, stop the pumps, close the selected valves, seal the container, and release the approved foam water system. The goal is not only to suppress the fire, but also to stop continued fuel flow and contain contaminated discharge. Containment is part of the fire response, not an afterthought. Before an incident, verify the leak cable, housekeeping, and drainage controls. Fuel-compatible seals, hoses, valves, and filters must be correct, while ventilation, the fire panel, and foam supply remain normal. Once detection is confirmed, alarm locally and remotely, stop transfer and polishing pumps, close the required valves, and prove feedback from the motor, valves, damper, and emergency shutdown system. For suppression, complete only the approved warning and delay, then prove foam water pressure and flow through the specified devices. During recovery, keep drains isolated, recover fuel and foam water, inspect the container and equipment, replenish supplies, retest, and authorize the fuel and fire systems separately. This slide presents the interface matrix for fuel storage, generator operation, and fire protection systems. The central idea is that every command must connect 4 things: the initiating condition, the generator or system state, the physical result, and the evidence that proves it occurred. Inputs include leak, level, interstitial space, heat, flame, and smoke signals. The matrix also accounts for generator run, load, cooldown, and ventilation states, along with local manual emergency shutdown and the listed criteria for releasing suppression. The expected outputs are equally specific. The system may stop a selected transfer pump, close identified valves, approve a generator action, place ventilation into fire mode, activate alarms, release the designated suppression system, or isolate drains where that configuration is adopted. The final layer is proof. Local hardwired feedback and controller indications must confirm the action, while the FACP, BMS, EPMS, and SOC maintain synchronized clocks and logs. A named evidence owner signs both containment and restoration status. That assignment turns a command into a traceable, reviewable event rather than an assumption. This slide presents the quality gate synthesis for the fire protection system, and it shows how each stage must connect before the system can be accepted and maintained. We begin with the inputs. The survey and system state are frozen, creating a controlled baseline. Next, the OEM model output is checked by hand, so the model is not treated as an unverified assumption. In the field, the as-built condition must match that exact model. Testing then confirms performance through FAT, SAT, and IST, with each stage required to pass. Finally, the approved restoration is recorded, creating a traceable closeout record. The most important control is the change control interlock. Any change to an opening, pipe, nozzle, cylinder, foam component, pump, temperature basis, or fuel control sequence triggers a formal impact review and recalculation. In other words, even a seemingly limited modification cannot bypass the quality gate. The system must be reassessed against the approved model, tested as required, and documented before the change is accepted. This module focuses on recovery and restoration after a spill, fire, or suppression system discharge. The objective is not simply to clean up and restart. Return to service only after the fuel system, generator, suppression equipment, and environmental controls have all been accepted. The recovery sequence is deliberate. Secure the area, clean and remove contamination, inspect affected systems, test their operation, and authorize return to service. At the site level, that means controlling access, preserving incident evidence, recovering contaminated liquid, foam, or firewater, and checking bunds, drains, interceptors, and potential environmental impacts. Equipment recovery requires an OEM inspection of the engine, exhaust, fuel package, and electrical systems. Damaged hoses, filters, detectors, nozzles, and operated devices must be replaced, while fuel quality and atmospheric safety are confirmed. Finally, restore system capacity by refilling or recharging foam and water mist supplies. Test valves, pumps, ventilation, detection, and interfaces. Close the impairment only through the proper process, and authorize power restoration separately from standby duty. Terms such as ESD, UST, FACP, OEM, and IDM define the key controls used throughout this work. This module focuses on Section F, testing and evidence, with the goal of proving fire protection functions progressively, from the original design through integrated testing. The systems in scope include the tank, transfer arrangements, IG-100, water mist, and foam water functions. The sequence shown here is important because each stage builds confidence for the next one. FAT, SAT, and IST are not isolated events. They form a connected path of verification. Factory acceptance testing checks what can be confirmed before equipment reaches site. Site acceptance testing then verifies installation and site-specific operation. Integrated systems testing brings the functions together in the intended chronology, so interactions and dependencies can be observed. After testing, restoration returns the system to its required operating condition. The learning path follows that same logic. Establish prerequisites, use safe simulation, test the integrated chronology, close defects, and finish with as-left proof. In other words, evidence is developed progressively, rather than collected only at the end. This slide presents the commissioning path for fuel storage, the generator, IG-100 foam and water mist systems, moving from the tank all the way to an integrated emergency response. The central idea is progressive testing. Each level builds evidence before the next level begins. The commissioning sequence runs from design and factory testing through installation, site acceptance, and integrated systems testing. At L0 and L1, the team confirms the approved hazard basis, fuel schematic, containment approach, equipment listings, and certificates of compliance. At L2, factory testing verifies the controller, emergency shutdown, suppression logic, fault behavior, and event text, with certificates tied to the exact components. L3 and L4 then shift attention to the installed system. Tanks, piping, vents, drains, detectors, nozzles, and access are inspected, followed by pressure and leak checks, level and pump operation, valve and ventilation tests, and safe suppression simulations. Finally, L5 integrated testing proves generator response, local autonomy, alarm chronology, containment, and recovery. L6 closes remaining defects, trains operators, and hands over as left evidence. This creates a defensible record from initial design intent to operational readiness. This slide brings together the FAT, SAT, and IST test families for fuel storage, generators, IG-100, foam, and water mist systems. The central acceptance principle is simple: prove the intended action, and prove that no unsafe side effects occur. For fuel systems, testing covers tank and interstitial leaks, level indication, independent high-high overfill protection, filling and transfer functions, return paths, pressure relief, and duty standby pump operation. We also verify valve positions, local emergency shutdown, power loss behavior, and control faults. Fire testing simulates heat, flame, leaks, and smoke detection. It also confirms water mist pump performance, flow, pressure, relief, alarms, and safe release. For foam, the focus includes concentrate identity, proportioning, valves, discharge, and the containment path. Integrated testing then demonstrates generator run and load response, alternate paths, safe shutdown, and the correct chronology across the FACP, BMS, EPMS, and SOC. We also confirm local autonomy during network loss, drain isolation, spill recovery, reset, and complete as left restoration. Together, these tests show that individual systems, interfaces, and recovery actions work safely as one complete protection system. This slide presents an example generator fire response test script with a clear sequence: prepare, execute, and restore. The central principle is never create an uncontrolled standby power outage. Testing should use controlled fire inputs, an approved load contingency, and either isolated suppression discharge or a safely simulated functional surrogate. During preparation, I would approve the test mode, load plan, impairment controls, and abort criteria. I would also verify that fuel systems, valves, ventilation, and suppression are in their normal condition, while synchronizing the evidence that will be collected. During execution, the generator runs at the approved condition. The scripted inputs may include a simulated leak, a confirming fire signal, and a manual emergency shutdown, or ESD. The test then proves the expected load response, shutdown, fuel isolation, ventilation action, and suppression feedback. Restoration is just as important. Before resetting anything, inspect the system, clear every output and feedback, and restore valves, pumps, fans, drainage, and suppression readiness. Finally, retest normal and fault states, close any defects, and confirm standby availability. The supporting terminology includes UST for underground storage tank, FACP for fire alarm control panel, and OEM for original equipment manufacturer. This slide defines the acceptance evidence pack for fuel storage, generator systems, IG-100 foam, and water mist protection. The central requirement is that the record set must demonstrate safe fuel containment, reliable generator response, and protection systems that can be restored after testing, impairment, or an event. The first category is design proof. That includes the approved fuel schematic, inventory and chemistry information, hazard register, engineering calculations, and the approved cause and effect matrix covering emergency shutdown, generator states, and suppression responses. Test proof then confirms that the installed equipment matches its listings and certificates, and that pressure, leakage, calibration, hydraulic, functional, and integrated tests were completed. The chronology should be synchronized, with defects, retesting, and final as-left conditions clearly documented. Finally, operations proof shows that the systems can be managed over time. It includes transfer, spill, hot work, impairment, and inspection procedures, along with spare parts, OEM manuals, environmental closeout, restoration records, training, drills, baseline settings, and management of change documentation. Together, these three evidence streams provide a defensible record of safety, performance, and readiness. This slide organizes acceptance evidence across three stages: FAT, SAT, and IST, with the owner and responsible parties clearly identified for each. The key principle is that each test must demonstrate the intended function at the appropriate level of integration. FAT, or factory acceptance testing, is led by the manufacturer with the CXA. It focuses on equipment-level behavior, including pump and valve logic, cylinder and release panel operation, and the bladder or proportioner. SAT, or site acceptance testing, is performed by the installer and CXA after installation. The evidence shifts to site conditions, such as pressure and interlocks, door fan and venting performance, and remote pressure or concentration measurements. IST, the Integrated Systems Test and Handover, brings the owner and AHJ into the process. It verifies system-wide responses, including fuel shutdown, alarms, zone logic, changeover, emergency shutdown, and effluent recovery. The final rule is important. A safe surrogate may replace a destructive discharge only when it proves the exact same functional and measured objective. That keeps testing safe without weakening acceptance evidence. This module focuses on Section G, Operations and Assessment, and how fire protection performance is managed throughout the asset lifecycle. The goal is not simply to install a system and move on. It is to keep the system ready, understood, and capable of supporting safe operations over time. The slide highlights 4 connected activities: inspect, transfer, drill, and improve. Inspection confirms the condition and readiness of the system. Transfer focuses on controlled fuel transfer, with attention to how that activity is managed within the operating environment. Drills help people practice their response, while also revealing gaps that may not be visible during routine work. Improvement closes the loop by using what we observe and learn to strengthen the overall approach. The learning path is operate, monitor, learn, revalidate, and improve. That sequence is important because operations change, conditions change, and the system must be reassessed rather than assumed to remain effective. Together, these practices address suppression impairments, environmental recovery, drills, and ongoing change across the data center's lifecycle. This slide focuses on the governance that keeps fuel storage and generator systems safe throughout their lifecycle. The central message is simple: discipline transfer, inspection, housekeeping, and change control prevent most fuel incidents. Routine work starts with inspecting tanks, vents, hoses, valves, trays, drains, and interceptors. Engine, turbocharger, and exhaust areas should remain clean, with leaks and fuel quality recorded. During a transfer, the activity must be authorized and attended. I need to confirm the volume, maintain communications, verify bonding or earthing, and check the high stop, drainage isolation, and spill materials before fuel begins moving. Protection also depends on testing leak and fire detection, emergency shutdown, valve and pump feedback, and generator status. The listed foam or water mist package, its supplies, and its containment path must be maintained exactly as specified. Finally, improvement comes from trending leaks, overfill alarms, level drift, valve faults, and system impairments. Any change to fuel, rooms, logic, or equipment requires revalidation, and incidents should lead to updated drills. Together, these practices connect operations with inspection, testing, and maintenance, or ITM, and create a repeatable cycle of inspect, transfer, test, trend, and improve. This slide focuses on what happens after an incident and on the routine governance that keeps the system reliable over time. The life cycle is straightforward: operate, monitor, learn, revalidate, and improve. But each step depends on disciplined control. During transfer, governance, filling, bonding and grounding, and verification of spill materials must be authorized before work begins. During recovery, access is secured, foam or firewater is recovered, and extinguishing agent is replenished only by the appropriate authority. Change control is equally important. Any site modification that affects software, logic, or enclosures requires the system to be revalidated. If the system is impaired, normal and fault states must be retested before it is declared ready again. Post-incident review should turn observations into practical improvements, while routine monitoring helps identify issues before they become failures. The central message is simple. Most fuel incidents are prevented through disciplined transfer, thorough inspection, good housekeeping, and strict management of change. Governance is not a one-time response. It is the continuous process that preserves protection and operational continuity. This workshop and knowledge check asks me to build and defend a credible response to one fuel-related scenario, with continuity, safety, and environmental controls all addressed. The goal is not simply to describe an emergency shutdown, but to prove that the response works from detection through restoration. I begin by choosing an event, a pressurized spray, day tank overfill, fill spill, or tank and dike incident. Then I map the fuel source, flow or pressure, ignition hazards, generator state, and drainage path. From there, I define the ESD by identifying which pump stops, which valve closes, and who owns both the command and the feedback. I also need to confirm whether alternate power or cool down is available before isolation. For suppression, I verify that mist, foam, or water spray is listed for the exact hazard and enclosure. I identify the required ventilation and shutdown state, and explain how discharge will be contained and recovered. Finally, the quality gate confirms acceptance criteria, safe failure, witnesses, evidence, and a restoration owner. No uncontrolled fuel, drain, or reignition path can remain. This module closes with a practical view of fuel fire safety as a coordinated chain, not a single device or response. The objective is to move deliberately through prevent, detect, isolate, suppress, and recover. A weakness at any point can affect the steps that follow, so the system has to be considered from fuel inventory and ignition sources all the way through containment and environmental restoration. From an engineering perspective, that means mapping every fuel path, drainage route, hot surface, ventilation condition, and generator state. Suppression must be listed for the exact application, rather than selected by assumption. During commissioning, the focus is proof. Teams need to test levels, leaks, valves, pumps, emergency shutdown, ventilation, and generator response. They also need to demonstrate foam or water mist hydraulics, local autonomy, operating chronology, and containment. Any defect should be documented, corrected, retested, and supported with restoration evidence. In operations, prevention continues through controlled filling, fuel quality, polishing, hot work controls, housekeeping, and maintain detection and suppression supplies. Finally, drills should include spill events and running generator scenarios, carried through recovery. These disciplines turn a design into a dependable, maintainable system. This final slide consolidates the references and governance that support Module 10A. Use only adopted codes, applicable environmental requirements, OEM guidance, and listed suppression data. That includes Indonesian authority requirements, AHJ and DAMCR coordination, relevant NFPA, ISO, and FM standards, plus approved software and manufacturer documentation. Lifecycle control is equally important. Maintain schematics, manuals, hazard registers, inspection and testing records, environmental documentation, and restoration records. The intended outcome is confident selection, integration, testing, and restoration within approved application boundaries.